Okay, so all of you know what elliptical shape is. It's just like, you know, a circle slightly deformed, but actually there is a very precise definition of an ellipse. And basically you can define it as follows. Imagine two fixed points, the two foci. And then you want to determine a set of points in the plane such that the sum of the distances of each point is the same for all the points on the curve. So you take a point on the curve which is an ellipse, you measure its distance from one focus to the other, you add them up, and then for all the points on the ellipse, that sum of distances has to be the same. It has to be one value for point A and the same value for point B, and so on. Any point on an ellipse has to have this property. You can actually make it by having a board, a wooden board, then you put in two nails, you tie to those two nails a slack piece of string, you take the pen, you make the string taut, and then you just move it until you complete the curve. And the resulting curve is an ellipse. Now, the fact that he realized that was quite a feat, because as you can see from this overhead, where things are drawn more or less to the scale, if you look at the planetary orbits by naked eye, you would swear that basically they are perfect circles. But they are not. They are actually slightly deformed circles by a few percent. The biggest deviation from a perfect circle, so-called eccentricity, is for planet Mercury, the one that is closest to the Sun. It is 21%. For all the other planets, it is less than 10%. Okay? For the Earth, it's 1.7%, less than 2%. Okay? And also to realize that the Sun is not at the center of these curves, but actually slightly off center. But nevertheless, he was able, the data were so accurate that Brahe collected, and Kepler worked so meticulously on those data that he was able to actually realize that regularity. So here, a little bit about ellipses. The number that tells you how deformed an ellipse is relative to the perfect circle is this number called eccentricity. And the way it describes the shape of the ellipse is follows. Each ellipse has two symmetry axes, the long one and the short one, right? And half of the longer axis is referred to as semi-major axis, and half of the shorter axis is called semi-minor axis. And then basically if you multiply the length of a semi-major axis with eccentricity, then you get the distance of the focus, one or the other, it doesn't matter, from the center of the ellipse. Okay? So if eccentricity is 0, that means that the focus is right at the center, both of them, and in that case you get a perfect circle. So a perfect circle has 0 eccentricity. If you increase it, right, then your curve becomes more deformed, and as eccentricity increases towards 1, the curve becomes more and more squashed, right? More and more elongated. So it is this number eccentricity that actually characterizes the shape of the ellipse. Okay, so if I have an elliptical curve, Then it has a longer symmetry axis and the shorter symmetry axis. And half of the longer symmetry axis is called semi-major axis. And here are the two foci. In the case of a planet, the sun is sitting at one of the two foci. And then if I multiply the size of the semi-major axis with the eccentricity, I will get the distance between either one of these two foci and the center of the ellipse. So when eccentricity is 0, then we have perfect circle. And as I mentioned before, except for Mercury, the eccentricities of all planets are less than 10%. For it, the eccentricity is about 21%. Now, as a planet moves along its orbit, there are 2 points when it is going to be, one when it's closest to the sun, and that point is called perihelion. And then another point is when it is at the greatest distance from the sun, and that is referred to as aphelion. And now, for the Earth, it is at aphelion, at greatest distance from the sun, but the variation is small, under 2%, is on 4th of July. And it is near the perihelion in January. So in fact, the Earth is closest to the sun when it's bitter winter in the northern hemisphere, right? And it is at the greatest distance from the sun when we have summer in the northern hemisphere. So once again, the seasons on Earth are not caused by variation in the distance between the center of the Earth and the sun, but because of that 23.5 degree tilt of the Earth's spin axis and the fact that over a period of few centuries, it basically doesn't change its orientation in space.